This is a video, an Abaqus tutorial, where I will show how to model and run the analysis, view some results for reinforced concrete beam. Simple supported reinforced concrete beam. And the modeling will be performed by two different ways. First, the rebars will be modeled as solid, and then the rebars will be modeled as wires. And after performing these two analyses, the influence of the stirrups, so the shear reinforcement, will also be included, but that will be done only for the case of the reinforcement modeled as a wire. So beginning, what I like to do is to, you can see you click this button here when you have open, and it goes to the temp profiles. So if you just go to set work directory under the file tab, and you can change here to wherever you want to go. So I want to go here. Okay, and now I can click open again and click on the small hammer here, and it goes exactly where I want. So I will just give a name. I will say reinforced concrete beam solid rebars, and I will click OK. Actually, I clicked open, but what I wanted to do was to save. Please excuse me, and I will write here reinforced concrete beam solid rebars. But it's good to know how to open in the folder that you want. So now we are going to start by building our parts. The first part is the plain concrete beam. That will be a 3D element. We can set here the approximate size as 1000. Click solid here, deformable, click continue. We get the part module open. So now we can just take this tool over here, this button, the rectangle, and just click on any 2 points to create a rectangle. Now we are going to modify the dimensions by clicking the dimension tool here, add dimension. For the width of the beam, we will use 300 millimeters, and from now on all the units used will be newtons and millimeters. So these 300s again are millimeters, and for the height of the beam, 650 millimeters. And now we can click the small X here, so we finish specifying the dimension, a large zoom right here, and click done. And for the depth, we will choose 10,100 millimeters, so 10.1 meters. You will see why. Okay. And now the beam is ready. We will need some other parts as well, so we can double click on parts again and create support plates, or support plate, only one, which is also 3D and deformable solid. Approximate size will be 300. Continue. Actually, it doesn't make much difference what number you write there. So here we just gonna draw the rectangle again, and we will dimension the bottom part as 100. The height will be 10, let's say 20. There's the eraser here, so you can click it and then delete the dimension property. Click done. You can choose another one and make it 20. Now you can click on the X, click done, and specify the depth as 300. Okay, so we have the supporting plate. And we have two more parts. One part is a phi 20 with approximate size 50, doesn't matter, and it's also 3D solid. Continue, and this will be a circular cross section. So pick a perimeter point for the circle or enter XY. Maybe the best would be to take the center of the system for the center of the circle, and just draw the circle anywhere. Afterwards, pick the dimension tool, add dimension. We select the center of the point and the point on the circle that is already defined. You can click outside and specify here 10. So 10 being the radius of the circle in millimeters, which will give the diameter of the circle of 20 millimeters. Then we can click on the X and click done. And specify again the depth as 10,100 millimeters. Okay. Yes. And the last part that we will need is a phi 10, which will be the compressed reinforcement, and phi 20 is the stretched fiber reinforcement or the tensile reinforcement. Phi 10, and click continue. We can draw the circle again. Click somewhere, doesn't actually matter, and then click somewhere else. Pick the dimension tool, click the center, click the point on the circle, and click outside. And here we can write 5, which is the radius in millimeters. Okay, and now this is phi 10 because the diameter is 10 millimeters. And click on the X, click done. Here we can write 10,100 millimeters again, and click OK. And now we have our parts, so we can go build our instance. But before doing that, maybe it's better to define the materials. And the first material will be C1620 concrete. And the properties are for elasticity, elastic, the Young's modulus 29 multiplied by 10 power 3, and Poisson ratio 0.18. Okay, and then plasticity. We will choose concrete damage plasticity, and we will write the standard parameters, which are Abaqus default parameters if no values or 0 values are introduced here, but I will just write them. So it's 31 degrees for the dilation angle, eccentricity 0.1, V0 FC0 ratio 1.16, K, capital K 0.667, and the viscosity 0. Now the compressive behavior and tensile behavior have to be specified here. And in this figure, you can see right here the real behavior of concrete, and here you can see the approximation that we will use in this model. These values are obtained by plotting this table here, but in Abaqus you only have to use the inelastic strains, and the inelastic strains are obtained by subtracting from the total strain the elastic strain. and this Excel file will be in the description. But in our case, we will only use this model. So we will have for the concrete 20 megapascals for the compressed yielding stress and 1.8 megapascals for the tensile yielding stress. But the file will be in the description, so if you want, sometimes the analysis gives problems with complicated structures. If it's something more complicated than a concrete cube, it doesn't work, but you can try, and you can just leave a comment, see if you get some result. Getting back to Abaqus, we write here for the compressed behavior 20 for the zero inelastic strain, and for the yield stress 1.18 for the zero cracking strain. 1.8, sorry, and 0 cracking strain. Yes, so now we can click OK. The density, actually we can also define the density of the material, but for static analysis, which we will perform right now, it's not necessary, because the mass matrix is not used in calculation for static analysis. Do you want to define it anyway? Okay, so we will not define it, and see what results we get without defining the mass density. Okay, so now to define another material, this will be steel S275 or something like that. So maybe write, to be consistent, S275 steel. And mechanical elasticity, elastic. The Young's modulus is 210,000 megapascals, and the Poisson ratio is 0.3. And plasticity, we define the yielding plateau for both compressive and tensile stress as 275 megapascals for zero plastic strain. Okay. Now the materials have been created, so we have to assign the materials to our sections. So we double click on sections, and we create a concrete cross section, homogeneous solid, and we click continue, and we choose the material C1620 concrete, and just click OK. And now we create another section which will be called steel cross section, and it's solid homogeneous with the material properties of S275 steel, and click OK. Now going under parts, expanding the tab for Phi 10, we find here section assignments. So we double click it, select the regions to be assigned a section. We just to make sure that when we click on the part appear in the window. So if you select plain concrete beam, you have it to the right. So make sure you double click the part that you want to go to, and then you go under section assignments, and just select the part. You can see the edges are highlighted, so you click done, and the section will be steel cross section, and OK. And now you can see it change color, so the section has been assigned. Going we have to do this for every part, so we go now to Phi 20. We can collapse, or not collapse, we can just squeeze it back, and now we can expand Phi 20 and click on section assignments. Click on the part, and then done, and select again the steel. It's changed color, so it has been assigned. Now we go to plain concrete beam, double click on the plain concrete beam part, and then section assignments, click on the beam, click done. Here we choose concrete cross section. OK. Now we go to support plate and we go to section assignments, click on the plate and click done, and we choose steel cross section and OK. Now we have assigned the section with the pertinent materials to all of our parts. OK. Now we can start building our instances. It's a good moment to save the work process. So you just click the floppy here to save. So what we will do is expand the assembly tab and double click instances. And we will choose all of them by holding Control and left clicking on all the instances. And just leave dependent for the moment and click OK. Yes. What we will do is that we will suppress everything initially, but not the plain concrete beam. And now we can work a bit with the plain concrete beam to position it exactly how we want to have it. And we want to have it along the x-axis, and y will be upwards and z will be lateral. So what we will do first is that we will rotate it 90 degrees. Click here on rotate instance, this button here, select the beam, click done, and then select the start point for the axis of rotation, this one, and then ending point, this one. And the angle is 90 degrees here by default, so you can just click enter. And don't forget to click OK or enter again, or I think the middle click works as well, because if you click something else, you will lose the process. So just click OK. Now we will translate the beam, so the corner of the beam will be in the center of the system of coordinates. So click this button here, translate instance, click on the beam, and click done. Starting point will be this point, and the ending point will be the center of the system of coordinates. And click OK. So now we positioned our beam in the way that we wanted. Okay, now we can suppress the beam for a moment. So just click on plain concrete beam, suppress. Now it's where we want it to be, and we can click on support plate and resume. And we have it right here. So what we want to do is to move it. So we will click on translate instance, click on the instance, click done, and click this point here. And then click the second point as the center of the system of coordinates, right here. And click OK. And this is how we want to have it. But what we want to do is also to create a linear pattern by clicking this button with 9 squares. Let's click it, and then select instance to pattern. Will be this one. Click done. You have this little window here, and we only want to have on this direction because this will be our supports for the beam. We will choose the offset distance as being 10,000. So the beam will be 10 meter long from support to support. Okay. Now let's see if we resume the beam, what kind of job have we done in terms of fitting. A bad one, obviously, because they need to go underneath. So we're just going to suppress the beam again, click or select both instances, and then, or no, we shouldn't select it first, we just have to click on translate. Now select both of them, click done, and start and ending point is this point, and the ending point is here. And now I'll click OK, and now I can resume again the concrete beam. Now it looks much better. Let's check the other one, the other side. And it looks that it fits perfectly. Okay. If we choose here in this tab, which is by default assembly defaults, we can select materials, for instance, and you can see that the supports are drawn with a different color, a different material. But we will keep it here assembly defaults for the moment. Now we are going to suppress again the concrete plane beam, the support plate, and the new created support plate, and we will resume phi 20. Having that, we want to rotate it first to have it along the X, so we click rotate, click on the instance, and then done, and then select a start point for the axis of rotation. And this might be a bit tricky, we might need to put something back, and select the end point, and yeah, we need to resume one of the plates. Maybe we just resume this plate, the second plate, so we have it there, and now we can rotate it. We just click on rotate, select part, done, and select the start and ending point for the axis of rotation. And we know that the start and ending point for the axis of rotation has to be this point and this point. Default value here is 90 degrees all the time, so just click enter and OK. And let's take a look of the position of the reinforcement right now. It's well, not exactly good, so let's just try to rotate it again. Click rotate, click on the instance, and then go on the plate, and we have to rotate it right now along the z-axis, right? Okay, so we go here, and this is the starting point, and this is the ending point, the axis of rotation, and click 90 degrees and OK, and let's check it right now, and now it looks fine. It's just in a completely different position, but we will translate it. So click on the translate the instance button, click done, or maybe not done, just click on the translate button again, click on the instance, now click done, and go take the middle of the center of the circle. Just click on the center of the circle and select the endpoint for translation vector, and right now just go to the center of the system of coordinates. Just click there and OK. Yes, and that's how it's supposed to be. We can for the moment suppress again the plate. So suppress. And you can see we have our reinforcement in the center of the system of coordinates along the x-axis. And now we will create a linear pattern by this button here. Linear pattern. Do you want me to wait a bit? Linear pattern. And just click on the instance, click done, and the offset will be just a moment, will be 76.667, and there will be 4. So there will be 4 reinforcement with a distance of 76777, but I think we should have left the plate because now we need to define the direction again. So resume that plate and then click again the linear pattern, click on the instance, done, and click on, we can write here 76.667, and for direction we just click here and select a line for the direction. We can just select z-axis, that's fine, and we will have 4. Okay, that's perfect. Just click OK, and we don't need the plate anymore. I think I have deleted the plate instead of suppressing it. No, it's there. So where is it? There's one supporting plate and the other one. Oh, okay, the other one is here. All right. So we suppress it back, and what we want to do right now is to translate all these instances. To translate all these instances, so we just click on the translate button, translate instance, and select all of them, and click done. And the starting point is 0, 0, 0, so we can just click here, OK. And the ending point is what we will do. We will translate on X. We will not translate at all, but we will translate on Y by 35, and on Z by 35 millimeters too. Okay, and okay again. And now they are positioned where they're supposed to. So now we can suppress them. So 520, 520, 520, 520. Suppress all of them. And now take the 510. 510, and there has to be another 510. Oh no, it's only one because we haven't created the linear pattern yet. So we can just resume the 510 and rotate it. Click on rotate, click on the instance, and done. And here apparently you cannot click on the axis. Yes, so we need the plate. Support plate 1, resume, and we are just gonna keep it there because it seems like we need it all the time. When we rotate it, I don't know, I think we have done it before, but we could have just chosen the axis. But right now we need to define the axis by 2 points when we rotate the instance. So click on rotate, click on the instance, click done. And now we can see that it needs to be rotated along. So if we want it on the y-axis, or along the x-axis, it needs to be rotated along y. So first point is this one, and then second is this, so 90 degrees. Okay, and it's somewhere here right now. We can click translate, select it, click done, select the center, and the center of the system of coordinates, and now click OK. And now we have it where we want to have it. What we will do now is create a linear pattern. Click on the linear pattern box here, click on the instance, click done, and now is the place where you can just click on the axis. You just click flip direction here, and you can just select here the axis. Here you don't need to select 2 points, but when you rotate the instance, apparently you just need to select 2 points. When you select the direction for creating the linear pattern, you can just click on the z-axis, and the offset here will be 240, and we can just click OK. And now we'll translate all this to instances. Click on the translate instance, select these two, and done. And now we can say 0, 0, 0 starting point, and the ending point will be 0 for x, for y will be 620, and for z will be 30. And click OK, and OK again. And that's where we want to have it. And now we can just visualize what we have done. We can just resume everything. Maybe just for the moment, let's just resume everything but the plain concrete beam. So everything of the but the plain concrete beam should be resumed right now. And we can see the supports and the rebars. You can see everything very, very well. Now we can save the process, because it seems like so far we have done a really good job. So click on the floppy disk box so we save the database model. Now we can just resume the concrete beam too, and by a brief eye visualization, it looks symmetric, so we can say that it is how it's supposed to, how we thought to be. And right now we will make every part as independent, and so we will mesh. So we will merge all the parts in one part. So maybe we don't need to make them independent actually right now. So instance, and then merge/cut. There is a last step here. We click it, and we can write here combo. We retain the boundaries, and we suppress the original instances. Don't delete them, because maybe you make a mistake and you want to still have them. And merge the geometry and click continue. Select the instances to merge. What I recommend here to do, you have a box instances, and you can click it and you can select them from here. But from my experience, what's the best thing to do is just click on the instances, and what you want to click first is that you want to first click on the steel. So click on the steel, just hold Control, click again on the other rebar, I don't like how it looks. I will start again. I will click Escape, Instance, Merge, and I will retain the boundaries, suppress the original instances, merge the geometry, and click here Combo. I will click Continue. So I click the rebar, click again, yes, so don't hold Control, just hold Shift, click, 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 and finally click on the concrete beam. Okay, and now click Done. And now to check this right now, we can just go to assembly defaults and write materials. So we can see now that the colors are the ones that we wanted to. So the merge was conducted in a good way. But now we have to assign as well a tie condition for the plates. So maybe this could have done as well by just including everything in the merge. So if you just delete this combo for a bit and resume everything, you could have also inserted a tie connection between the plates and the beam, but the simplest way to do it for this kind of problem is to just merge them in already existing, cannot be overwritten. Okay, just write combo 1 and click continue. And we click on the rebar, 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 rebar. Click on this plate, click on the other plate, and click on the beam. And now done. Alright, so now we have the combo with everything included, and the materials look fine. So we can just go here to where we had materials and choose assembly defaults back. Okay, so now we can save. Now let's just apply the load. So the load that we will apply is in a step that has to be created. So the step is called static, and the procedure maybe static step, and procedure type general and static general. Just click continue. The time period will be 1 second. What's this?
The load.
The load, okay. And then the initial and the minimum and the maximum. The maximum number of increments we will just write 100,000, and initial 0.01, and minimum just leave it as it is. And maximum 0.05. You want like this? Okay, so we choose for the maximum 0.05. But what was here by default for maximum? 1. Okay, so you say if it goes over 0.05, you want it to stop.
No. If it goes at if it's bigger than 0.05, it will still just choose 0.05, the maximum increment.
Okay. Yes. Yeah, so we can just click OK here. Okay. And we define the step, and now we can go under loads, and name it capital Q in the static step, and it's a pressure load. Continue. You can just apply it on the top surface of the beam. Click done, and it's a uniform load with a magnitude of 16. No? So the magnitude here in newtons per square millimeters will be 0.053 newtons per square millimeters. So we just click OK. You can see that the load is also now represented on the drawing. So what is left to be done is to assign the boundary conditions and to mesh. But first we will do the mesh. And for meshing this model, we need to assign first some partition planes. So we can just here open the mesh module, and we will just go first to mesh controls, this mesh, and we will right click on combo and click make independent. Yes. And now we will assign some partition planes. One will be, so we just select the whole structure, done, and point and normal, click on this point here, and this is the normal, create partition, like that. Now we select everything again, done, again point and normal, and we have this point here, and this normal, create partition, and now here select everything again, click done, point and normal, select this point and this normal, and create partition, and now select everything again, click done, point and normal, go in the middle, and this is the tangent. Okay. But what I actually don't like is that what I expected was to see everything with green, so everything could have been modeled as hex elements, which are 8 node deformable element. And we can see that only the steel plates have that option, and the rest of them have to be meshed with some other meshing technique, apparently. Now let's just finish the partition planes. So we will right now click on the XY plane, or the YZ plane, and now we can select this part here, and done. So we take point and normal again, take this point and this normal, create partition. Oh, and actually right now, what happened? Now it can be modeled as hex element after assigning this partition plane, which is very nice. Now we're just gonna select it again, and we are gonna click done, point and normal again, and it's the center, and this is the normal, and create partition. Now it's very, very nice. So you see how important it is to define partition planes before initiating the meshing process. Now I'll do the same thing for the bottom part. Just click on YZ again and select. Now let's think if we want to cut the plate too when we do this, and yes, why not? We go with everything. So select like this and click done, point and normal, select this point and this normal. Okay, and now do it again. Select done, point and normal, select this point and this normal. Okay, and now do it again. Click done, point and normal, select this point and this normal, create partition, then select again, click done, point and normal, this point and this normal, and create partition. Okay, and now we can see we'll still have some areas that we have to work on. We will right now select everything, done, point and normal, take this point and this normal, create partition, very nice. And now we select everything again, we click done, point and normal, we take this point and this normal and create partition. Okay, and now again we select everything, click done, point and normal, and we take this point and this normal and create partition and click done. And right now if we take another look from the side, you can see that everything looks nice and green. And what green means in the mesh module here is that it's possible to mesh it with hex elements. Yes, but a bit of extra work could be also good, but maybe to assign another cutting plane here. Yes, and maybe another one right here. And then point to normal, this point and this normal. Yes. And I will do another one here and another one here. And that will do it. So just select everything, done, point and normal, this point and this normal. Yes, and now select everything, done, point and normal, this point and this normal. Okay, and now we need to do 2 lines here as well. So done, point and normal, this point and this normal. Okay, and now select everything again, done, point and normal, this point and this normal. Okay, yes, and select again, done, point and normal right here and this normal. Okay, you see it takes a while, but if you work a bit on the partitioning, that you can obtain some really nice meshes afterwards. Otherwise it'll be you will not have a symmetric mesh, and maybe even if you have a symmetric element, for not having a symmetric mesh, then you will not get symmetric behavior. So it's good to spend some time, even if it takes a while, to draw this partition planes. Okay, and one more here and one more here. So just select everything, done, point and normal, this point, this normal. Okay, and select everything, done, point and normal, and this point and this normal. And we will stop now. We are fine with this, and the reason for which these lines are not aligned is because the edges are aligned, so that's why. But the mesh will be okay as well, like this. Yes, so just to take another look from the other side, looks very well. Very nice. And now we can go back to the general view and mesh it. But we will need to assign also some transversal partition planes. So we need this view, and we can select everything like this, click done, point and normal, and it will be, and now there are so many elements and it starts going slowly. Click on this point here, create partition. We will need some cutting planes for our support, so in the middle of the plate, you see here there's this thick line. Oh no, not anymore. Okay, so just select everything, click done, and first point and normal, and just go for this point and this normal, create partition. Nice. And now just select this, done, point and normal, and now we go in the middle. So this is the middle of the plate and the normal, and create partition. Very nice. And now we have to do the same thing in the other side. So we select this, done, point and normal. We are here initially, this is the point, this is the normal, create partition. Very well. And then again, done, point and normal. Select the point, and that will be the middle of the plate, which is here. And this is the normal, and create partition. Yes, and some intermediate will be also nice. Maybe one here, and then one here, and then one even closer, and that will do it. So just go to ZX plane and select everything, done, point and normal, select the point here, take this point and this normal, create partition.
Maybe save the model.
Yes, I'll just okay, maybe I should just save it right now. Click on save. Now we will go here in this part, select like this, click done, point and normal, and we choose this point and this normal, create partition, and we're done with this side. And we go to the other side and create same pattern of partition planes, and then we are finished with the partition planes. So we need to do 2 more partition planes in the other side at half, and then again at half. Man, this beam is so long. How did you choose this length of the beam? So select this and then click done, point and normal, go for the middle and select this point, select normal, create partition, and now we go to this part here and just select everything, done, point and normal, and we select point and the normal and create partition. and done. Okay, we're just inspecting the element a bit. So now it looks fine, we will save it. And we go to the mesh, controls, select the regions assigned to be assigned mesh controls, and we select everything. And we click done. And you can see it's by default the green one, hex, which are 8 nodes, deformable elements. So we can just click OK here, and that's alright. And then we can go to the mesh, to the seed part, seed tab, and click seed instance. And we are asked about the approximate global size. We will choose the approximate global size as half. No, we will choose it. I'm just thinking. Let's see. Can we just view the plan again of the beam? Yes. So this is 520 here. Maybe just take it 40 or 50. Let's see what happens. And click apply. And OK. Yes, and now I click mesh and instance. OK to mesh part instance, yes. And now it'll take a bit because the meshing process is initiated. We can see propagating mesh seeds. So if it's gonna take too long, I will cut the video and I will come back to you after the mesh was assigned, and I will tell you how long it took. Okay, and this is our mesh, and personally I think it looks pretty fine. It's a very fine mesh, and the analysis might last 1 million hours. But you cannot fail unless you try, so we are gonna go to save right now and go to apply the boundary conditions. Okay, now it's saved, and we go to boundary conditions, double click here. No, it didn't. It didn't stack. It didn't stack actually, because I can just go through. Just double click. Okay. Yes. And now we will write for the first boundary condition. We will write hinge support, and in the static step there will be displacement rotation and continue. we can select this plane here, and then select here, and while holding shift, clicking all the lines.
But you're going to put it down here on the surface.
Oh, yeah, I was doing it wrong, so we have to go back, and yes, this is a good one, no? No?
Yeah, this is the steel surface. The steel
Are you
plate.
sure?
Yes.
Okay. So we go again to boundary conditions. We write HS from hinge support, displacement rotation, okay, and we click lines, holding shift.
Or maybe it's not this one also. Try to rotate it like this. I think it's down there.
It's down there, yeah. Is this one now?
This should be okay.
I'm sure now it's this
Yes.
one, right? Okay, so now we go to boundary conditions. Hinge support, and continue. Click here, here.
Are you going to put on the whole surface?
No, not on the only on this line.
Okay.
Here, 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 here. And then the distance between the supports will be 10 meters. Yes, now we can click done. And it's U. Okay, so let's see, 1 is X, and we want U2 and U3 block for the hinge support. And everything else is alright. Ramp here, and okay. And now we impose this one, and we go to the other end. And here, we click again on the boundary conditions, and we write SS from simple support. Displacement rotation, continue, and we have this line, holding shift, this line, this line. If you're afraid not losing this counting of the lines and you make a mistake, so you need to go to select everything again, just create some sets. You have the sets table on the left in a tree, so you can just double click on sets, and you can just choose the sets, and after having the sets you can just click here and you choose from the sets where you have to assign the boundary conditions. But we don't have that many, we can just click them for the moment and click done here. And here we choose U2 0, and everything else is the same, and just click OK. Yes, and now we go back to our general view and save. One last thing to do before running the analysis is to check the field output requests tab. So field output request, you can just double click here, and you want we have the step 0.01. So do we want the step every increment, do the output, or maybe every 10 increments? If we have 0.01 the step, then, and that is the maximum step, or no, it's the initial step. Yeah, so let's say we'll have that step and we will get 1,000 points, right?
Yeah.
So do we want 1,000 points, or are we fine with 100?
I think it's okay, 100.
100, and it's gonna be much faster, the analysis as well. So you just write 10 here.
Okay.
You understand how it's
Yes.
going? Exactly. So everything, stresses, strains, displacement, forces, reactions, and contacts, that will remain the same every n increments 10. So click OK. Now we can double click on jobs, and that will be named say solid job with maybe just solid job, and we are gonna click continue. Here from the parallelization tab, use multiple processors, and I'm gonna leave it 2. My processor is Core i5, but I don't know if it's if I should write here 2 because it's only 2 cores, or maybe 4 because every core has one real and one virtual core on by itself. But I'm just gonna leave it 2 to be sure, and up to 90% of the memory, so I better close everything else that I have open before running the analysis. And that's it, and I think I'll cut the video and I'll see you on the other side of the analysis, and I will save it again before. And you can just right click and click submit, and I'll see you on the other side. These are the results. So let's check the for me this is first, and of course it's blue because the range is up to 191 megapascals, but the concrete only goes until 20. So if you want to check this one and click limits, and you specify and you go to 20. Okay, and then you will see the Farmisa stresses in the concrete. If you want to see the normal stresses, you can go and take from -20 to 0, and then you can see, you can also click this button here, and you can see the compression normal stresses. Let's click this button and just let it swing. Wow. Okay. Yes, and now you can see it, this sort of nice animation with the compressive normal stresses in the concrete, compressive normal stresses in the concrete. If we stop it right now, we can have this tool here for X, and we can see that first we need to go to auto compute again, and we apply, and we have with green in the tensile part, and so we have the bottom reinforcement. We have there around, no, something is wrong here. If we go in the middle, so 50-50, and we are in the middle, and we write here S11 again, and here from -80 to 200. Yeah, but we have this bluish here, which is around 200, or no, it's around 60 actually, 60, and the green, this should be actually red and should be around 200, but it was like that before, and I don't know what changed right now. Let's see the displacement, U2. You are actually showing me, yeah, auto compute here and apply.
Oh, I know why.
What happened?
Because you did the animation and you
Yes.
stopped it at some time,
Yes, exactly.
so you have to do the animation to
Yes.
let
And now
it
we have.
finish.
So we just if we just stop the animation now, or when you click this button, don't swing it. Just play it once, and then it's gonna stop. Yeah, like we did it now. Okay. And now if we but now you see it also stopped somewhere, I guess. If we because it's still minus 32. So if you click the
Maybe do,
again,
yeah, but change the animation type. No, not, yeah, like this. Yeah.
yes, and now it's like it's supposed to be minus 22 millimeters, and the normal stresses we go to S1 and go here and auto auto compute apply. Okay, and we cut it, go to the middle, and now you can see with the blue the compressed reinforcement, and with the red the stretched reinforcement, with the values 191 megapascals for the stretched reinforcement and 64 megapascals for the compressed reinforcement. Okay, so that's about it. If you just animate it again and click U2, and you can see, and with these arrows here we can go to every frame back. Yes, this is beginning and end. Very well. And this is our solid model. Now we will do the same thing, but we will model the rebars as wire. So I will start with the old model. Where the beams are modeled as solid, and I will click Save As, and I will go for wire. I will just write wire instead of solid. And yes, I will overwrite it because I had it before, but I don't like it how it is. So I'll do it again. It's done. So now we have our parts. Combo that we will delete. Combo 1 we will delete as well. And we will also delete phi 10 and phi 20. And what we have is the plain concrete beam and the support plate. Alright. And now we also have the materials defined. And in assembly we delete the combo, and we will resume all the instances.
Yeah, this happens because you deleted all the rebars.
Yeah, but actually I will just delete.
No, but now you're deleting the support also.
No, it's okay. I have the parts anyways.
Ah, okay, then it's okay.
Ah, yeah, I have to keep those, no? Here.
Yeah, you can keep
Yeah.
them.
So I will just delete like that.
Exactly.
Very well. So now we have the supports, and I've done that. I used the old solid model, solid rebar model, to go for the wire model, so we don't need to place the supports in the exact position, and we just have it, and we have the material defined for concrete and steel in the same way as before. And right now we are gonna save it. We have here wire, so we don't have the solid, so we mess up everything that we have done before. We have wire. We go to the floppy button and we click, so we save. Database has been saved. Alright, so now we are going to parts again and create a new part that we'll name 520, and it'll be deformable 3D wire, yes, approximate size 1000, and we're gonna click continue and choose the polyline button right here. Click it, just connect 2 points on the vertical line and click enter. Or just click escape, maybe. Done. No, not done. We should have dimensioned it before, but I think we can do this right now as well. So we go to section 2 features, wire and section sketch. So we go here and now we can dimension it. Just click the dimension tool, the dimension button at dimension first point, last point, and click outside, and the length is 10,100 millimeters. And now we are done. The feature has not been regenerated. To regenerate the feature, select feature, regenerate. Okay, so we select feature, regenerate. And now it's longer. Alright. What we have to do now is to create another part, which will be also wire, and it will be named 510. Continue. And the same way, click on any 2 points on horizontal line. That's done, and now click the dimension button, and it will be as well 10,100 millimeters. We can just click OK, X, and done. And this is our 510. Now we have to go to profiles. And we will define our profiles. We have a 510 profile, which is circular. Continue. And the radius will be 10. Okay. And then create another profile. We will name 520 profile, and also circular, and the radius will be 20. Right. Now under plain concrete, maybe just squeeze this up and go to 510 in the parts, and here there is section assignments. So double click on section assignments. First double click on the part, double click on the section assignments, select the part, click done, and here, alright, because we haven't defined proper sections yet, so we have to go to sections and create a beam section, and this will be wire, rebar, section. It should be a beam section, and click continue. We have defined the Poisson ratio for steel as 0.3 in the material properties, but since we are asked to do it again here, we will do it again, and the material name will be S275 steel. The rest remains the same. Click OK. Profile name doesn't remain the same actually, because we have to choose the profile name, obviously, of course. So we'll do it for both of them. Both of them have the same material properties still here. So we will just write OK, and then do it again. Actually, this wire rebar section could have been wire rebar section 510, and the other section wire rebar section 520, which is beam as well, and here just choose steel, and here choose profile 520, and that's it. Click
The
on
Poisson ratio.
Poisson ratio, yeah, just choose 0.3. Okay. And now we have the sections, so we can go to section assignments under the parts. So click on, double click on the part, and then double click the section assignments, select the part, done, and now we can select for 510, which doesn't actually matter what we select, but just to be consistent, so choose here 510, and okay, and then go to 520. Yeah, maybe just some unnecessary work. It could have been only one, and just with the generic name of let's click on the part, click on the section assignments, done, just with the generic name as a wire rebar section, maybe. Let's see, wire section 520. Okay, yeah, so now the section assignments are done. Now we have to assign some orientation for our beams as well. So we double click on the orientations and select it, and just click done, and you see choose use default orientation or other method, and you just click this button, and we are gonna use what appears here first, and we're just gonna click OK. Yes, and we do the same thing for the 510, so just click on orientations, click on 510 first, double click 510, then click on orientations, and select, click orientation, selected, done, and then use default orientation or other methods, and just click OK as it is. Alright, now we have to insert the wires in our instance, so we just save the process right now, and we double click on instances. Yes, and we want to add 510 and 520. Apply. Okay. Just cancel right now because we have added already. We can suppress for the moment the plates and the beam. So suppress, and now we can see the rebars. Maybe we can go to this plane right here, and it's obvious that we need to rotate them. So let's start with this one. Just make sure which one is it. Five, 10. So the bottom one is 510, and the top one is 520. We suppress, we work with the 510 for the moment. We click rotate, click the instance, done. Select a start point for the axis of rotation. It's gonna be this point. And actually what I'm gonna do is select the end point for the axis of rotation. The axis of rotation has to be the z-axis. So I'm just gonna write 0, 0 and just 1 here. Hopefully it will work. And 90 degrees. And it worked. Or not really. No, maybe undo. Cannot actually undo it. Let me just delete it.
Just delete this. Yep. And then add it again.
And then add it again, exactly. So add phi 10 again. And actually it's along x-axis, so don't need to do anything.
Are you sure?
Yeah, this one is you just need to translate it to
yeah.
the center of the system. So click on translate instance, select the instance, done. Click on the endpoint and click on the center of the system and OK. And now it's as it's supposed to be. So now we're gonna create a pattern. Click on the linear pattern, click on the instance, done. And the distance between them will be 240 and the direction will be the z-axis, and there will be 2. But something is wrong. Yes, and here it has to be 1. Okay, so now I have this. And now what you have to do is to translate everything. So translate instance, select both of them, done. And now we will choose the origin, so we can just click enter, and for the endpoint of the translation vector we will choose for x will be 0, for y will be 620, and for z will be 35.
Yes.
Yeah, I think it's alright. It's 35.
Yeah.
Okay, so we can just click enter and OK, and we can see that we have them right here. And that's very good. For the moment we save and we suppress them. Now we resume phi 20 and we will just move it first of all in the center of the system. So click on translate, click on the instance, done. The start point and the end point, and OK. And now we create a linear pattern and click done. Here don't have anything. Here the direction will be the z-axis and the distance will be 76.667 millimeters, and there will be 4. Okay, so that is it. Click OK. And now we have to translate it. So click on the translate instance button and select everything. Click done. Select the starting point and yeah, which is the same as 000 here, or not writing anything. So just click enter.
And that was the
Oh, that was the endpoint. Okay, so I have to write again the endpoint, which will be 0, and for y will be 35, and for z will be also 35. Okay. And okay, and now we have our phi 20. And we can see how it looks together with our phi 10. Looks very well. Okay, so what we want to do right now is to mesh them, maybe.
The constraints.
Yeah, maybe just to seed them before making the constraint. Well, maybe just make the constraints as you said. So just resume everything. Or creating a set would be nice before resuming. So we go to sets. Not steps, just to sets. Yeah, so double click on sets. And here we will name the set rebars. And click continue. And now we select everything here and click done. And now we have the set of rebars. Now we can resume everything. And we will embed the reinforcement in the concrete and create tight connections between the supports and the plate. But for creating that kind of supports, we will need partition planes. So We need a partition plane right here. Dependent part cannot be edited. That's alright, so everything will be independent here. Make independent, perfect. And now we will create a partition plane. Done. Just select everything. Don't worry, it will not go like for the solids. We will not partition that much, but
choose partition plane. You just selected that.
point and normal, and to be this point and this line. Okay, and same thing on the other side, and that's all the partitioning that we have to do. Done. Point and normal. Click here and click on the line, and that's it, the partitioning. Now let's try to tie the supports to the beam. So we will need to suppress the beam a bit, and then we can define some surfaces, and we have supports surface, and click continue, and we have this surface here, and holding shift we go to the other support and click the surface, and just make sure both of them are selected. They are, and we click done. Now we choose another surface, but first we have to resume the concrete and suppress the plates. And we lost the partition plane, of course. Yeah, so what we will do is resume the plates. We go to features, and here we can resume the partition cells too.
And maybe you can just hide the support plates.
Yeah, but if I hide the support plates, I will lose the partition plates.
I don't think so.
What do you mean? How to hide them?
Just click,
Yeah.
right click,
Yeah.
and just you don't have hide.
No, there's no hide here. But I can translate them. So I can just to translate them a bit, and I click on the partition, translate, and then click the partition plate. This is the support plate, and then I click the other support plate here. So I'll show you what I'll do right now, and just make sure both of them are selected again. They are, and then I'm gonna click done, and the starting point will be here, and the end point will be here, just for a moment. And now we have the supports plate and the partition plates. So we can create, just to make sure our surface for the supports is created. Yes, we can see it here. Now create the other surface, which is beam bottom surface. Continue, and obviously it will not be the whole bottom of the beam, but only this surface here together with this surface here by holding shift and left clicking. Make sure both of them are selected. They are, and click done. Yes. Now we can move the supports back. So translate, instance, click on this plate here, click on the other plate here, and click done. Now we have start point right here and end point right here, and okay. Now we have the partition planes as well, but now we also have the sections. See the beam bottom and the support surf, and they show the same section because now they are in the same spot. And what we want to do right now is to go to constraints, double click on constraints, and define supports to beam, and it's going to be a tie connection. Yes, exactly. Continue, and we choose the surface, the master type surface. I'm going to go to surfaces, and the master type surface will be beam bottom surface. I'm going to click continue and choose slave type surface, and that will be support surface. Click continue again, and here I'm not doing anything, and just leave everything by default and click OK. And now we have this constraint. So now we have to embed the beam in the concrete, the rebars in the concrete. So we will just go to constraints again, double click and choose embedded rebars, and there's gonna be an embedded region, and I'm gonna click continue, and sets below may contain elements, shell faces or wire edges. I'm just gonna click the rebars and which methods for the host region, select the region, and that will be everything basically. Yeah, selecting viewport, and then I'm gonna select this part, and this part, and now I selected everything that is concrete to embed the reinforcement into, and click done. And here I just leave it by default and click OK. Okay, now we can see that the rebars are embedded by having these small circles here all around. Yes, and now we need to check the load, because we had it from before, so just to see how it is, and it's not good, so press yes to continue editing the load, and we want to continue editing the load. The magnitude remains the same, but we have to choose the region where it's acting. So the region is this point here, this section, this surface here, and this surface right here, and we'll click done, and now it's okay, and we have the load. Very well. And now we go to the boundary conditions, and we will need to define the partition plane for assigning the boundary conditions, because they are lost as well. Yeah, so I will just delete them because they don't work anymore, because the partition planes at the middle of the supporting plates are not there anymore. So this one will disappear, and double click the boundary conditions, click H. First going to the partition planes and select cells to partition right here. Done. Point and normal. This point, this normal. Create partition. Going to the other one. Done. Point and normal. Select a point. Select a normal. Create partition. And done. Okay, now we have to, we can go to the boundary conditions. Double click it. Just hinge support, let's say first. Click continue. Go in the viewport, select this one, this line here. Click done, and the U2 and U3 are 0, and click OK. Now we go to double click boundary conditions again, and we write SS from simple support and displacement rotation type, and click continue, and go here, click on this line and click done, and U2 will be 0 and everything the same, so we click OK. Now we can take our general view, and we have our boundary conditions and our load. Okay. What we need to do now before running the analysis is the tool mesh, and the rebars need to be seated, and then the global mesh has to be applied. So let's just go to the mesh module to see what we have here, but first let's save the process. Mesh, and everything is nice and green. How lovely. Meaning that we can mesh everything with hex elements. So first I will suppress everything but the rebars, and I will seed the rebars. So I have the plank concrete and supporting planes that I will suppress, and these rebars will be seeded. This one done, and approximately global size I will leave it 1000. So every meter, maybe choose 500, so it's every half a meter.
Yes.
And click apply and OK. There we go. Now we can resume the other things, and we resume the partition cells too. And I just want to make sure at this point that we still have the load and the boundary conditions. So I double click on the load and everything is fine. I double click the boundary conditions and actually they are fine because we can see them. They are over there. They highlight with red when we double click them. Yes. And now we can go again can go back to the mesh module and click mesh. Maybe just go to seed, because if it's with green it means that it's already assigned to be meshed with hex elements, which are 8 noded deformable elements. So we go to view and we go to seed instance and we select the instance that we want to seed and just click on everything basically, because and click done, and approximately global size will be
150.
100 and
because you got 4 here.
yes, but here is 300 and here is 650. It doesn't need to be meshed by squares or by cubes all the way. It can be other kind of.
Maybe 50 like the other.
To choose 50?
Yeah.
Like the other? Okay, let's just choose 50 and apply. Okay. So now we can just go to mesh and mesh instance. And done. Yes, and now I have the mesh, which looks very nice. So we can save our process. We go to click the floppy button. Now it's safe. Yes. And now we can run the analysis.
Yeah.
So this will be named wire job, and we click continue and okay. Just to check what we have in field output request, just to squeeze up all these things that we have here, and the field output request we're gonna keep it tiny, every 10 increments. Okay. You don't know how long it's gonna take, so
Yeah.
and now save it again and I will submit it. Regions of the part 520 have not been assigned a beam orientation. Wire bar section 520 picked. Use the assign beam orientation in the property model to assign a beam orientation. Regions in the part 510 have not assigned. So now we are being told that we didn't assign an orientation, but actually I thought we did, so it's kind of weird, but we will do it anyway. Go to parts and section assignment, and we have orientation here. Yes. Maybe to read about the error again. So click on submit. In the property module, beam orientation. Okay, so we go to the property module and we click assign beam section orientation. Select the region. Okay, this is done. And again. Okay. And then you go for 510. Assign beam section orientation. Click it. Done. And okay. Yes. So now we go to the wire job again. Right click. Submit. And maybe we have assigned it for 520 two times, because now we still get error for 510. Dismiss. We go to 510. Go to the property model, assign beam section orientation and select it, done, and okay again. And now we squeeze it back, we save, we go to just double click on the assembly to see them all and go to wire job, right click, submit. Actually guys, you know, if you just don't make any mistakes, if you don't work. So we made a mistake here. For profile it was a phi 10, which is radius of 5, so diameter is 10, radius is 5. So the stresses were very low. The formation stress is 56, the maximum, but that was because the diameter of the phi 10 was actually 20 millimeters, and the diameter of the phi 20 was actually 40 millimeters, because we inserted the values for the diameters in the radius box. So here is 10, and that's phi 20. Okay, and now we can run the analysis again. We can just and actually I don't like to overwrite analysis, because I think it's a very good thing to do. So I will just write wire job, and here like good.
Maybe you can increase the step to 0.1, just so it takes less
to increase the step to 0.1.
Yes.
So I will click here, continue. Okay, and I will go to steps, static step, and incrementation. I will just write the maximum 0.1. Okay.
And now maybe you can also do the static step, go back and just put the output.
Yes.
And put
to take the output every step.
Yes. Or maybe each 2 steps.
Okay, let's take it every step. But I'm not sure that it's not gonna take 10 times longer if you put 1 step instead of 10 steps.
Maybe you can put 2 steps then, and you'll get 5 points.
1 or 2, doesn't matter. Let's put 1 and let's see what happens. You want 2?
If it's 1, then it takes 2 times longer than 2.
Okay, and just write 2. Okay. If it is like this, that we say that.
Yeah.
I don't know. I thought that before I remarked that if you choose a 10-step field output, then it's taking way much shorter time than taking 1-step field output. But I cannot bet on it. You can just leave a comment, say what you think about this. And now going again to wire job good and submit. Yes, and the analysis is now completed. You can see here between brackets, and we can view some results. Click dismiss and then right click and click on results, and let's see some displacement. We go to U2, and we can see that we have the maximum displacement of 20 millimeters and 20.1 or 20.2 millimeters, and when we modeled as a solid we had 21.8 millimeters. So 20 millimeters and 21 millimeters, 22 millimeters, they are very close to results which we obtained in both of these approaches. Also, if you want to see some normal stresses and let's say you want to see the concrete compressive behavior, you just go and write here 0, and here you write minus 20, 29. 20, and apply. And now we can see that what is with gray is in tension, and what is with the color in the legend box is in compression. Or if you want to see some formations, and formations are always positive, so if we go to 0 from 20, you can click OK. Now we can see formations stresses in the concrete, and you can actually see something. But you can also go back to the defaults, so auto compute and choose S11, and there is this tool here to cut, and you can cut through the plane, and you can see that the blue so that it's compressive stresses in the top rebars, and with the red tensile stresses in the bottom rebars. Yes, and the values here are also close to the ones obtained by modeling the rebars as solid, and I invite you to go back and check the results. And now I just want to show something else. If you click this button here, then you can go here in this range, and you can choose maybe if you want the middle, and you write 50-50. It's actually the number that you have to write to go to the middle of the beam, exactly, and to read the results for whatever you want to read, whatever stresses are. Yeah. And this is it. We can use some animation, and we can view the photomesis from 0 to 20 in the concrete. Can apply. Yes, and this is not photomesis. I have to choose photomesis. And now we can see very nice the variation of the photomesis stresses in the concrete. Okay, now we stop the animation, and we can create some display group manager. We just click on display group manager and create one, and we will insert only the rebars. So add, and we name it display group 2. Okay, so now I have display group 2, and in display group 2 we see only the rebars, and you can see the photomesis stresses in the rebars like that. But we have to go back to the legend box, and we click the inbounds of the legend as default, and click apply. And now it's going as supposed to, from 0 to 174.6 megapascals. Here it's written 1.1, but here you can see it's actually right. So that's why you thought it's wrong first, because you will hear it sometimes doesn't show well, but in the legend box it shows right, so it's alright. Also, if you want to see the rebars more with the real thickness, you can just go to options and display body, and here you have a
view.
No, not you have to go to view and ODB display options, and here you can choose render beam profiles scale factor 1 and apply. The basic plot option render beam profiles is supported only in deformed or undeformed plot modes. Alright, so you can just see that in this deform mode or undeformed mode. So you cannot see contour shapes on beam with when they are rendered. You can just see the deformed shape. Yes, and if you don't want them, then you can clearly see that. So I untick the box and click apply, and now they change the thickness. Okay, that's just something saying that you can see the actual thickness. Okay, so now we just go to the next step, and we will try to model the stirrups too. We double click on
Maybe make a save as.
Yeah, we go back to the parts module, and we will save it as same name, but we will include an underscore at the end of the name, and we will write stirrups. Is it double R?
Yes.
Yeah. Okay, and just click OK, and now we have it. So what I will do now is define stirrup, and I will name part stirrup, and it's a wire and planar, yes, and then just click continue. Here just take the rectangle, click on any 2 points, draw the rectangle, then click the dimension tool, click on the bottom part, and this will be 250 millimeters, and click on the vertical part, and this will be 595 millimeters. Yes, and we are done. And this is our stirrup. What we need to do now is to define a profile for our stirrup. So the profile for our stirrup will be phi 8 profile. It should be circular, so we continue, and the radius will be 4 because we use phi 8 for reinforcement. For the shear reinforcement, we use phi 8. Okay. Yes. And now we can go to section assignments. We just select everything. Done. And the section will be, maybe we should make a new section before. No, don't save the changes. We go to sections and we add a new section, and we also the beam section, but this will be the stirrup section, stirrup cross section, and it will be beam section. Continue. The Poisson ratio will be 0.3. Material will be S275, and the profile name will be phi 8 profile. And okay. And now we can finally go to stirrup and section assignments. Select the whole stirrup, click done, and stirrup cross section. And you can see here it appears beam and S275 still. You cannot select here the concrete section, of course, because that's for 3D created. You can only select the sections that are created for wire elements, now not for solid. So you just create stirrup cross section. So just select stirrup cross section and okay. Yes, now the cross section is created. And the changed color, this light green here, it says that the section has been assigned. And now going to assembly, expand it and double click it. We will just add the instance, so add the stirrup, and okay, and we will suppress for the moment everything but the stirrup. Yes, now we need to rotate the stirrup against the y-axis, so click on rotate, select the stirrup and rotate it, done, and against the y-axis, right? So this point and this point, 90 degrees, exactly, like this. Very well. Now what we want to do is to move it in the center. So we click here OK, and now we're gonna translate it. We're gonna translate the whole stirrup, done. And this is the starting point, and this is the ending point. Okay. What we will do now is that we will translate it again. Done. And this will be the starting point, 0, 0, 0, so just enter, and the ending point will be 0, 21, and 21. So it will be in the middle of the beam section, in this way. Okay, okay again. Hopefully at least. And what we will do now is that we will create linear pattern. It looks distorted here, but it's very straight actually. So linear pattern, just select it, and we will have first ten, 10, 10. Yeah, I think it's 10, 10, 10. So
is that like 9?
no, let's see. I think it's like this: 9 spaces, 11 spaces, but they are 10, 10, 10. So done. And
we have to change up that one, the offset here.
yes, so here
Now change here
we
something.
don't need, and here we need the offset of 250 for the moment, and we will do 10. Yes. So now I have 10 stirrups like this. Okay. Now we do another linear pattern with this stirrup here. Done. And this step will be this time 500 millimeters. And we will do another 10. Okay. And now take another linear pattern, this stirrup, click done, and the step will be again 250 and 10 stirrups. Okay. Looks good.
Maybe you can add the beam.
What we need to do now is that we need to translate everything to the right a bit. So
Yes.
on x-axis.
Yeah.
And that will need to be done with 10 millimeters.
Yes.
Yes, because the thickness of the plate is 20.
Exactly.
20.
So
No, it's not 20 actually. It's 50. It's 100. So 20 is just the height.
so we move it.
Yes, so 50 millimeters, everything moves to the right. So translate. Done. Starting point 0, 0, 0. And ending point on x is going to be 50 and the rest of them remain 0. And okay. So now you can see that it's a bit displaced from the center of the system of coordinates. It's like this. We can actually choose the view from here, and we can see. And we can also lose the panorama. So now we can see that they are all aligned, and distances are fine. Set the panorama, or not panorama. I like to say panorama, but it's called perspective. Okay, now it's a good moment to save.
Maybe we can resume the concrete beam to see how.
Yes, and now we resume the everything.
No, just the concrete beam.
Just the concrete beam. Okay.
To see through it.
And to see through it. And it doesn't look good. Doesn't look good at all. Doesn't look good. So
You need to add 2 more here.
Yeah, actually I needed to add yeah, I said I had 10, but there were 10 without this one and this one.
Yes.
So I needed to add 2 more here. So what I can do right now is not too much, then start again from here.
Now we can translate this with 100.
Yes, I can translate.
Yeah.
This. No, I have to suppress the beam again. So I can translate this.
Yeah, translate it with 100.
Yes, go this. Done. Select the starting point, 0, 0, and then I go
With 1000.
1000.
Yes.
Yes. On X.
Yeah.
Okay. And then I create a linear. Oh shit! I have to do it again now, but it's no problem. I'll just translate this ones and done, and starting point 0, 0, 0. That's what I was talking about. Just don't click escape or something. Just click enter or a middle click or click OK after you submit the command. So here just click OK. And now I can just create a linear pattern with this one here. Done. And there will be free, and the direction will be X. 500.
Yeah.
No.
Put here.
Okay, and okay,
Looks good.
looks good. Now it's very well. And save it.
Maybe just say again. Resume the concrete.
Yeah, just resume the concrete beam to see how it looks, and it looks very well.
Yeah.
Let's resume the plates too. plates are there, so it looks like it's in the middle.
Yes.
Let's check the last one.
Also looks.
Also looks like it's in the middle, so it looks like it's a very well constructed reinforced concrete beam. Let's suppress it back for a moment and create a set with our stirrups, because we will need it in the future. So we just go to sets, double click sets, and here is stirrups. Continue. Select all the stirrups, done. And now we have our set. Now we can go and resume everything that we had here. And if we go to view and assembly display options, we can render the beam profiles. But it's only the longitudinal reinforcement for some reason that appears thicker. I don't know why the stirrups don't want to appear thick too. Well, it is how it is for the moment. Just click back. Both of them? Doesn't make sense. Okay, so we leave it like this for the moment. And now we need to embed the or maybe to seed, and that I've been able to do before. So suppress it again, and now we can go to the mesh module, and we will seed the stirrups. Seed instance.
Make them independent.
Yeah, I have to make them independent. So we select the first one and hold shift, select the last one, right click, make independent. Maybe that's why they didn't show thick.
Maybe.
Let's see afterwards. And now we can seed instance, select everything, done, and approximately global size. What size are they? Just to check again, they are 250 by 595. So maybe just choose
50.
50. Okay, now they are seated. Done. So now what we do is let's go to the property module and just assign what beam section orientation. Just click it. Done, and leave it as this. And click OK. And OK again. Basically, there he's assigning the local coordinates for the section. And now we resume everything in the assembly module. I will save everything right now again, and
Maybe now try to see if we can see the cross section.
okay, now let's try to see. I was thinking to mesh first and then try, but we can try it right now too. So we go to view, assembly display options, and render beam profiles apply. And how wonderful! Yes, now everything appears. And actually, what I would like to check here is that the lines described by the stirrups, and maybe I should take this plane and lose the perspective. So the lines are actually touching but not overlapping.
Yes. Let's go a bit up.
Yeah, it looks like there's a problem here. So
We need to make the stirrups and here. We have to make them
but
wider.
are there so many lines?
Maybe this is just how it shows the thickness.
Okay.
So you need to make the stirrups a bit wider.
It's not even at the half. Let's check it again in the general view. You see, it's very well to check the beam render, so you know that you have done something wrong, like we know right now. Yeah, so it's clear that they are on top. So the longitudinal reinforcement is on top of the stirrup, so we calculated their length wrong. So I guess we'll just proceed like that. Or what do you think?
Yeah, kind of like that.
We go like that and just see whatever we get, and you guys get the idea, and you can do it the right way. You can just calculate the right dimensions that you have to assign, and then you'll see. Okay, so now we go to the mesh module, but we will lose the render for the moment. But it's very good to check the render, because then you can find mistakes that you have done, and you do it correctly. Just calculate the right dimensions that you have to have for your stirrups. This is just the way of the working procedure. So apply here and OK. Now we go to the mesh module. Click on the full here, and we just mesh, seed instance, done, and 50 and apply, and OK. Done. Oh, okay, and now going to mesh instance, and done. Done. And we have our mesh. Very well, and now we can just run the analysis, I guess, but just to check that the force and the boundary conditions are not altered. Yes, they are.
And you need to make some constraints.
Yeah, let's check the constraints.
Because
Yeah, let's first check that nothing is there anymore, but we can resume the partition planes, and maybe now they will be there. Let's see now. Support. Yeah, now they are there. All right.
is what you need to add
Yes, I will embed
the stirrups.
the stirrups, but just this is here too, and the load is here too, and the boundary conditions. Yes, they are there. So remember, guys, when you have partitions, you have these features, and you expand features. And here, sometimes the partition planes were making suppressions and then bringing them back. The parts in the instances in the assembly. Then the partition cells, they get suppressed too, and then you have to resume them if you want, because they don't get resumed automatically. So you resume them, and then you can have your boundary condition load and constraints that you have previously defined when you had the partition planes. Now double click constraints, and this is embedded stirrups, and it's embedded region, and click continue. Select the embedded region, we go to set, and we click on the stirrups, continue. Select methods of regions, and we click select region, and now we select in viewport, and we will click this one, hold shift, select this one, hold shift, select this one, hold shift, select this one, and hold shift, select this one. Now click done, and click OK. And now we can see that everything is embedded. So now we can save. Kind of sucks that the stirrups are not defined properly, but you get the idea. And now create a new job, which will be named wire and job stirrups. Continue. Let's check here too. And okay. And just to check something in the step. We keep it like this, right?
Yes.
And the field output we keep it at 2?
Yeah.
2. Okay. So we can just save again and run it. I click results.
No, I have to submit a new job.
Did I click
Yeah, you just clicked results right now.
results?
Yeah.
Okay. So submit, of course. The following part instances are not mesh. Plain concrete beam support plate. Unmesh widgets basically. Continue with job submissions. No. We go to the mesh module. And we mesh again. I think we embedded that was the problem, that we
Maybe.
embedded
Yeah.
and then the mesh went off. So
Oh, they're seeded.
yeah, but I need to write. Oh, it's 50 already. Okay. So mesh instance and done. Okay, now it's okay. So now I save again and submit. And it looks like this time we will not get any errors. And it started running, and I'll see you on the other side of the analysis. Okay guys, and now the analysis for the model with stirrups is done. You can see here completed. We dismiss the monitor and we right click on the job and click on results to see what we got here. And to see some von Mises stresses. They don't help much, but yeah, maybe we should go to see some deformations. So U2, which didn't change much actually.
Yeah. So this means that we don't have enough force. We don't have big enough force.
Yeah, but the stirrups should stiffen a bit more. The beam should add some stiffness. So the displacement in the middle, I would have expected to be smaller than 20 millimeters. But let's just if we create here a display group, a new one, and we just want the stirrups and the rebars, and we add them, and this one, display group 3. Like this. So the thing is that because this beam doesn't have shear forces that act on it basically, or not much, because it's subjected to bending. What it does primarily, it's subjected to bending.
Exactly.
Then the biggest stresses are, let's see some von Mises stresses here. S11. Sorry, S Mises. And here we can see that the stresses in the rebars are pretty low for all the rebars. They are close to They are close to the stresses in the concrete, around 15 megapascals,
Yeah.
and the stresses are much higher in the longitudinal rebars. So because this this kind of reinforced concrete beam is subjected mainly to bending. If it was instead of the beam subjected to uniform distributed load, if it was a column subjected to moving supports, or so subjected to an earthquake, and check my video with the earthquake. Just the link is in the description. If it was like that, then the shear would have a major influence. The shear forces would have a major influence on the response of the rebars by means of stresses. So then you could have seen there. I mean, if you use the rebars in that kind of analysis, if you use the stirrups in that kind of analysis, then you can see that the deformations are decreased because actually that structure that I have there failed due to shear. But here it's just subjected to beam. So what happens is that the beam undertakes mainly bending, not that much shear. So the displacement doesn't change that much. This would be the explanations why the displacement remains relatively the same when stirrups are added. So maybe create a column and try to move the supports according to some accelerogram, or just create a random accelerogram yourself and see what you get there. So good luck in engineering, and I'll see you next time.